I got it. Please go to our accounts just to confirm. I got it. Please go to our accounts just to confirm. Hello. Okay. I got it. Please go to our accounts just to confirm. Hello. It's causing a thing. Causing a thing.
Bluetooth mode.
Sorry. That's okay. Hello.
Okay, I can see you online. Yeah, on YouTube.
Oh, okay.
Okay, perfect.
I've muted the YouTube because it was lagging, so I don't know.
Just talk and say something.
Hello. Okay, no, it's working. All right. It's lagging, so I don't know.
Just talk and say something.
Hello. Okay.
Perfect, I can hear you. That's it, good.
Okay.
Thanks.
Connected.
Hello.
Hi.
I don't know if you want to email everyone who is who registered, because the link doesn't appear on the calendar.
What do you mean it doesn't appear on the calendar?
So like the event appears on the calendar, but it hasn't pulled through the link.
It's there. I got the link as well from the calendar.
Oh.
I added it onto the calendar. What is not happening though, it's not live. It's
Yeah, so you can't click it. So
but you can copy it and paste it.
Yeah, that's what I did. So just hope.
Okay, so if you do that, it works.
Yeah, it does.
We'll have to do that because I lack capacity.
And
we're live, ma'am. Hi, Jen. Lovely for you to join us. Sean says hi, Jen.
Hi, Sean.
All right. We should have mocktails and such today, being our first webinar of the year.
Mocktails.
So, imaginary mocktail.
Did it have to be mock?
Public space and all. Mocktail.
Yeah. It's so hot here. It's
mocktail and tea, everyone.
I promise this is coffee.
We trust We trust our community. That is coffee.
Cindy, you
This is
can
a-
Uber Eats us the mocktails next time.
Okay.
Yeah.
Okay. So our final webinar for the year, you have to come or Lebohang.
Oh no, definitely now.
Yeah. Then
I'm
we'll have
part of the
mocktails.
community now. I'm part of the family now.
I mean, I don't even know why you're having reservations about the podcast, because it would be great.
I'm not having reservations. I just didn't know about it when you spoke about it.
You haven't said yes.
I haven't said no either.
We are moving.
Okay, we're
This is
doing.
promising. Oh, okay. Mm. All right, we are about to get started. Hi, everyone, even the community that's joining us via YouTube. Good afternoon. Okay, so today we have Olebohang Molefe for our podcast, our webinar. Just a bit on who Olebohang is. She is a PhD candidate in applied mathematics and a lecturer at the Department of Finance and Investment Management at the University of Johannesburg. Her educational background includes a Bachelor of Science degree in Mathematics Science, an honors and a master's degree in applied science. She has several years in experience with teaching and mentoring undergraduates. Her research, which she'll share a bit about today, focuses on mathematical modeling of crime dynamics using systems of differential equations and drawing on concepts from ecology and dynamical systems to study interactions between communities, law enforcement, and correctional facilities. So this kind of work combines theoretical analysis. It includes stability and bifurcation, which is a new word I learned today, bifurcation analysis with numerical simulations to inform evidence-based policy and intervention strategies. Beyond her research, she is highly passionate about innovative teaching, science, communication, and changing negative perceptions about maths, and particularly in young women. Thank you so much for that. She is actively involved in academic development initiatives and is committed to making mathematics accessible, relevant, and impactful to both within academics and beyond academia. This is something that we're looking forward to hear about. Olebohang, you may have the stage.
Oh, thank you. Let me just switch on my video just to say hi so everybody sees how I look. Anytime now. Sorry, it's taking forever. I'm blurry, aren't I?
You are. Oh, there we go.
Hi, everyone. Okay, it's lagging, so I'm gonna switch it back off again. Sorry.
No problem.
Let me just share my screen. Screen sharing. Let's do that. And let's go into presentation mode. All right, can everyone see my screen?
Yes.
Okay. A very good afternoon to you all once again. I'm really looking forward to this talk, and I hope the next 30 to 35 minutes will be worth your time. Now, when people hear mathematical modeling or even just differential equations, many immediately think, oh no, this is definitely not for me. But this is not just about mathematics. It's about thinking differently about human behavior and social systems. We are all brought together here by one common purpose, and that is research. And what we are trying to get out of research is some sort of model. We want to understand how things work. And to do that, we build a model. And just because my model does not look like yours, it doesn't mean my model is wrong. It just means that mine is not useful to you, just as yours is not useful to me. And I guess that's where this quote from George Box comes from. And he says, essentially, all models are wrong, but some are useful. So, my research is based on population dynamics. This is the study of how and why populations change over time. This can be population sizes, age, structures, and species distributions, amongst many others. Mine specifically focuses on population sizes, and I analyze the interactions and movements between the different population classes. We'll hear more about these population classes when I dive into my model. These movements can be influenced by environments and interventions. For example, the spread of a certain behavior like violence, cooperation, and other social norms. It is very important to note that a population does not change randomly. It responds to some kind of pressure. Now, traditional methods are usually used for social sciences. For instance, interviews, surveys, narratives, and theories. While these methods help us describe the systems very well, sometimes we need to look at our problems from a different lens. Qualitative methods, like the traditional methods, they usually give us depth, meaning, and context. They tell us why something happens, while quantitative methods give us patterns, trends, and thresholds. From this, we can explore what happened next by predicting. We're not saying one method we're not saying one method is better than the other. We're saying that both methods need to be correctly understood and implemented so that our research makes sense. The main difference between qualitative and quantitative research is the approach. Quantitative research has a more objective approach. They use verifiable data that remains consistent regardless of who is observing it, whereas qualitative research relies more on people's feelings and opinions. In as much as our work needs to be factual, we can't deal with human behavior without taking human perception into consideration. And that brings us to mathematical modeling. First, we need to understand what exactly a model is. We can define a model as an abstract representation of something, or a pattern, or something, or a pattern of something that can be made, sorry. So we have different kinds of models. First, we have a physical model that is just a constructed copy of an object, like a model airplane or a model bridge. Then we have a schematic model, which is a means of visualizing a system or a structure. This can be done through graphs, charts, and diagrams. Then finally, we have mathematical models. This is just another representation of the behavior of real-world phenomena, just in mathematical language. We use equations, algorithms, formula, and theorems. There are many laws of nature that can be explained using mathematics, and human behavior is no different. Mathematical models make it possible to quantify the abstract behavior of some phenomena, and because of this, they are an indispensable part of the real world. The models help us understand why and how things happen, to make predictions using patterns and trends, and they provide insight into real-world problems to come up with optimal solutions. It is important to note that not all mathematical models fulfill all these objectives. Some models are purely constructed just to analyze, some are constructed just to make predictions, and some are constructed just to provide insight. Now, how does all of this work? We have something we call a modeling cycle. It is called that because we start at some place and we end up at the same place after this whole cycle has been completed. All mathematical models start with a real-world problem. This real-world problem is then translated into the conceptual world through cognitive activity. By cognitive activity, I mean we would imagine how and why whatever scenario it is happening. What we imagine is not always 100% true representation of whatever happens in the real world, because in these models, we make assumptions and we have some limitations. We then look at the model we conceptualized and then we analyze it. We then interpret the results from the analysis to make predictions, and then the predictions are given back to the real world. To help us understand the cycle better, let's look at the COVID-19 outbreak. For the real world, we first observed what was happening. We observed that this virus exists and saw that it was spreading rapidly. After the doctors and scientists thought, okay, so this exists, but how is it happening and why is it happening? This was now the cognitive activity that led to the conceptual world. And from this, they constructed a model for COVID-19 to understand it mathematically. Then they analyzed it. They played around with all the contributing factors to the spread of the virus and made deductions and predictions from that. These predictions were then interpreted back into layman terms and translated back into the real world. I don't know if you remember, but this is how the Gauteng government wanted to dig 1.5 million graves in 2020 after predicting that 1.5 million people are going to succumb to the COVID-19 virus. But as George Box said, all models are wrong, some are just useful. So that is a mathematical modeling cycle. We started in the real world and we ended up in the real world. Now, we have fundamental rules that we have to follow in the process of mathematical modeling. We first have to identify the object or the system that we want to model. Here, you think of a purpose that you want to use the model for. Why am I doing this? What is it that I am trying to achieve? Then we follow the process of mathematical modeling to determine the variables and parameters that we need in this specific model. Human behavior, amongst many other things, is quite complex to model. It is not always that we have all the facts or that we can use all the parameters in effect. Hence, we make some assumptions. From here, we can solve the model analytically or numerically. The results from the analysis are then interpreted and predictions are then made. And lastly, before we jump into conclusions and dig 1.5 million graves, we need to validate our results. This is usually done through experiments, and experimental data is then compared to the outcomes of the model to see if they match. Or the validation can be done intuitively. For example, in population dynamics, we can somehow get a result of a negative population size. Does that make sense? No. We can't have a negative number of people, right? This means something went wrong in the model. So using these principles, after validation, we can then go back to either the beginning of this flow diagram, where we then need to work on different objects and systems, or change our variables and parameters. Now, enough with all the background. Let's dive into my model to illustrate this mathematical modeling that we have been talking about. So now there are many kinds of mathematical models, and I use one that is called an SIR model. SIR stands for susceptible, infectious, and recovered. These are the kinds of models that are used for infectious diseases. Okay, but how? Now, everyone that is born falls into the susceptible class. I think I'm going to need my laser. How do I get a laser from here? Sorry, laser pointer. There we go. So when everyone is born, everyone falls into the susceptible class. Then once you contract whatever disease it is that we're trying to model, you then move on to the infectious class. Then after you've been in the infection class and you've been through some treatment, then you move over to the recovered class. So essentially what we do with our model is that we divide any population into different classes, and then we determine how we move from one class to the other. It is important to note that an SIR model is a very basic and surface level model, because essentially we're saying that if we have a whole population of people, say in Gauteng or UJ, let's just look at the population of students of UJ, we're saying that we can only divide the UJ students into 3 classes, being the susceptible, infectious, and recovered, which is not always the case. Let's look at the next model, the second model here, which is now called the SIRS model instead. So now, apart from just having the susceptibles, infectious, and recovered, we're saying that after someone recovers, they can go back to being susceptible and become infected again, right? Then in the third one, we have an SEIR model. So here we're saying that instead of going straight from being susceptible to being infectious, we're saying you can have a class in between the two that is called the exposed. This is where an individual could have been exposed to the disease, but hasn't been infectious yet. This is like this window period we have when someone is exposed to HIV, yet the virus has not yet been picked up in the person's system. Now, in my research, I model criminodynamics. This is the study of crime movement and behavior using differential equations. I am basically interested in how someone moves from being an innocent citizen and a member of the community to becoming a criminal, and how they move from being a criminal to getting arrested and going to prison, and how they move from being in prison to being rehabilitated, with the possibility of a rehabilitated criminal going back to becoming a criminal again, right? But how does someone enter this susceptible class? Like we said, just you being born puts you into this susceptible class. I am saying that any innocent, law-abiding citizen in South Africa, this population will be increased by some rate, and we'll call this rate lambda. This is now the birth rate of a certain region. So then we have the rate at which people move from being susceptible, innocent, and law-abiding to becoming a criminal. This movement happens by someone in the susceptible class interacting with someone in the criminal class, be it by being related to a criminal, being friends with a criminal, or just even seeing a crime being committed, or just a video of the crime being committed. That is why we have both the variables S here and C here, to illustrate that we need these two individuals to interact so that the movement from S to C can happen. So we call the rate at which this movement happens beta 1. So this is beta 1 because we have another rate at which someone goes from being innocent to being a criminal, which we'll talk about just now. All right. Then we have some function that depends on the number of criminals that can illustrate the movement from the criminal class to the prison class. So this is just noted as a function because there are so many factors that can contribute to this movement, and not all of them can be included. These are part of the assumptions and limitations that I spoke about earlier, but I'll also talk about this in a while. So now, in my PhD research, I am also looking at the dynamics inside of prison. So from this prison class here, I am going to divide my prison class into two other sub-compartments. So I am saying that in prison, I still have my susceptible prisoners, and these are just individuals that are innocently in jail trying to serve their time and leave. But then we still have corrupt prisoners, okay? These are the prisoners that are still committing crime, even though they are already in prison. It's crazy, right? But that's the reality. Thabo Bester is running a prostitution ring from prison. Just imagine. So after getting arrested, after being in prison, we have that people move from being prisoners to being rehabilitated. So here we're just looking at the certain percentage of individuals that come out of prison, that are released from prison, basically. Okay, then we're saying that this happens at a rate gamma. So after this happens, okay, so after these prisoners are rehabilitated, we are saying that there's a chance that these rehabilitated prisoners become criminals again after coming out of prison. We're saying that there's a chance that they become criminals again, and we will say that this happens at a rate sigma. That is the rate here. Okay, so we are all human, right? And we're definitely not immortal. So we all have some sort of mortality rate. But whether you're innocent or guilty, rehabilitated or not, we all have the same mortality rate. And this is represented by this mu here. So from the susceptible class, we're saying that people die at a rate mu. From the criminal class, we're saying that people die at a rate mu. From the prison class, we're saying that people die at a rate mu. And from the rehabilitated class, we say that people die at a rate mu. Okay. So looking at inside our prison dynamics, which looks scary, I know, yes, but this works just as I explained it up here. So let's start looking at the susceptible class. So we're saying that in the susceptible class, remember we had people moving from being criminals to being prisoners at this function F of C, whatever function this is that depends on the criminals. So we're saying that if this is the rate that people move from being criminals to prisoners, we're saying that a proportion row of this become innocent as they go into prison, or the rest of that proportion go into jail and immediately start partaking in criminal activity already, right? So that is the F of C here, going into prison. Then when we're in prison, we have, like I said, we have the susceptible prisoners and we have the corrupt prisoners. So once someone is a susceptible prisoner, after interacting with another corrupt prisoner, it is possible that this person that is in the susceptibles becomes a corrupt prisoner as well. And this happens at a rate beta 2 after the interaction between a susceptible prisoner and a corrupt prisoner, just as we had here. Up here where we said someone moves from being susceptible to being a criminal after interacting with that individual. So instead of the rate beta 1 here, that's why we have the rate beta 2 here as well. Or if someone joined the prison as a corrupt prisoner, it is possible that somehow they get rehabilitated inside prison and just go back to being a susceptible prisoner where they're just now innocently trying to serve their time and leave. Okay. So just as these prisoners are human, they also die at a rate mu for the susceptible prisoners and at a rate mu for the corrupt prisoners this side as well. Now, whether you're a susceptible prisoner or a corrupt prisoner, you can still get rehabilitated. And we're saying that this happened at a rate gamma. So we'll call the rate at which the susceptible prisoners are getting rehabilitated gamma 1, and the rate at which the corrupt prisoners are getting rehabilitated gamma 2. And that will come out to being gamma p here. Right. So now, how do we get to our differential equations from this model diagram that we had above here? So now let's look at our susceptible class alone. So now we're going to look at all the factors that affect the population size, what increases this population and what decreases this population, right? So we do that by coming up with something that we call a differential equation. So this differential equation describes how this population changes over time, all right? So we're saying if we have this population here S, and we try to see how it would change over time at this rate ds over dt. We're saying that this population increases because of this movement here. This population increases because of this rate lambda, and that's why we have this lambda over here. But this population decreases when people leave from being susceptibles to being criminals. They decrease because of this function here, because of this interaction here. And that is why it is included here as a negative, because this decreases our population size, beta 1 SC. And we also have another decrease here, which is mu S, and that is from the people dying. So that is the differential equation that describes the population of our susceptible class, okay? Now we move to our criminal class. Similarly, we need to see what factors affect the population size here. Which factors increase our population? Which factors decrease our population? So we're saying our criminal population increases by people moving from being susceptible to being criminals. And it was because of this factor here. And that is why we have it as a positive instead here. But it also increased when the rehabilitated criminals became the rehabilitated convicts became criminals again. And that is this sigma R over here. That's why we have that sigma R over here. And then we have this minus Q1C. So now mathematicians are very lazy. So instead of writing that my population decreased because of this mu C, which is what we have here, and because of this epsilon beta C, which we have here. So this epsilon beta C has now changed from the F of C, which we had earlier. Sorry, from this F of C, we now decided that we're just going to include two factors in this function for people going from being criminals to being prisoners, where epsilon now represents the rate at which these criminals are being arrested, and the theta represents the capacity of the prison, because if the prisons are full, we can't have people being arrested again. Right. So yeah, these are the two factors that decrease the population, the criminal population. So instead of writing them both like that, they both have a common factor C. So we just took that common factor C out to be left with mu plus epsilon theta. And this mu plus epsilon theta is now represented by Q1 because mathematicians are just lazy. They don't want to write everything like that. So these are the three factors that increase and decrease the population size of the criminal population. Then moving on to the prison clause, right? So in the prison clause, remember this is what we had for the prison clause, but we said we're not looking at the prison clause the way it is. We're going to divide it into two separate compartments, being our susceptible prisoners and our corrupt prisoners. Right. So now let's look at our susceptible prisoners alone. So in our susceptible prisoners, we're saying that this population increases by this factor here. This is people getting arrested, this row FC. But now remember, we said our FC is now epsilon theta. So this is what we have here, epsilon theta C. So our susceptible population increases using this term. Excuse me. And also using this movement over here, where people that are corrupt prisoners then somehow get rehabilitated while in prison and just become susceptible prisoners again. That also increases our population size, which is why it's a plus here. Then now we need to look at the factors that decrease our population size. And this is the people that move from being susceptible prisoners to being corrupt prisoners using this term over here. And that is why it's got a negative here, because our population is decreasing because of that movement. Then we have two other movements that come out, and that is the prisoners dying at a rate mu, or the prisoners being rehabilitated at a rate gamma 1. So just as I explained here in this red block, mathematicians being lazy, instead of writing minus mu SP minus gamma 1 SP, they just represented it as minus Q2 SP. Then moving on to our corrupt prisoners population. We're looking at all the factors that increase this population. This is this factor here that comes from being a criminal after being arrested. So you can be arrested and become corrupt immediately, and that is this term over here. Or the population increases by this movement from being susceptible to being corrupt after this interaction, and that is this positive term over here. And again, we've got two terms. Oh no, it's three terms. Then we have three terms that decrease the population of the corrupt criminals. And that is the mortality rate mu. So we'd have minus mu CP. That is the rate at which a corrupt prisoner becomes susceptible. So we'd have minus alpha CP. And then again, the rate at which the prisoners are rehabilitated, which is this gamma 2. Then we'd also have a minus gamma 2. So the minus mu CP minus alpha CP minus gamma 2 CP was then simplified to just minus Q3 CP. So these are all the factors that decrease the criminal population. The corrupt prisoners population, sorry. Then lastly, we have the rehabilitated population. So now all the factors that affect this population size are the gamma P, which we separated into the susceptible prisoners and the corrupt prisoners. That's why we have the gamma 1 P and the gamma 2 P. These are the two factors that increase the population of our rehabilitated individuals. Then the two factors that decrease this population are this sigma R, which is the rate at which these rehabilitated prisoners became criminals again, even after rehabilitation, or this mu R, which is the mortality rate. And again, mathematicians are being lazy. So instead of writing minus mu R and minus sigma R, they simplified it to minus Q4R. A lot of mathematics, I know, right? I'm sorry. So from this model diagram, which is our schematic what was it? Our schematic model. So we first drew up a schematic model, and this schematic model has now brought us to our mathematical model. So now you see how just describing the movement between these these six different classes has now brought us five different differential equations to describe how all of these populations change over time, where Q1, Q2, Q3, and Q4 are described down here. Okay. So even though I said you might not necessarily need an intricate knowledge or background of mathematics to understand all of this, I see how you'd probably be scared once we get to this point. But to be honest, it only gets worse from here. It gets worse from here, but it's still doable nonetheless. If someone could do it before, nothing stops from you doing it either. So now after you come up with your differential equations, you then move on to your model analysis. So in our model analysis, this is when we need to determine the positivity of solutions. So now because I am dealing with population dynamics, we need to ensure that my solutions stay positive, because now my solutions are here to illustrate a certain population size or how a population changes over time. I can't have negative solutions because that means we have a negative population, which is not really possible. Then I need to test for the boundedness of my solutions. I need to make sure that my solutions do not, like my populations at some point will not increase all the way until positive infinity, because we do have some sort of capacities that cannot be reached when we deal with population dynamics in a certain community or environment or region. Imagine if we had an infinite number of criminals or an infinite number of susceptibles and stuff. Where would all these people stay? Where would they live? This is where overpopulation would then come about. So to avoid that from happening, we need to test that our solutions are bounded. This is part of the validation processes that we had in our mathematical modeling cycle and the principles of mathematical modeling. Sorry. So then after this is done, now the real mathematics starts, where you need to now determine our equilibrium points. So our equilibrium points basically, how do I describe? So our equilibrium points basically show us what would eventually happen to each population over a certain time. We want these populations to be stable at a certain point. We don't want our population to keep increasing, decreasing, increasing, decreasing. It's either we want it to be constantly decreasing to zero or increasing just to a certain point, maybe a certain capacity that we have of a population in that certain area. Okay. So in us determining these equilibrium points, that will be us solving our model, and that will help us make our predictions, where we say, if I increase the arrest rate, this is what's going to happen to my population of criminals. They're going to decrease until a certain point. Relatively speaking, it cannot be zero, because I don't think we live in a perfect world where we have zero criminals. But we can have like a really, really low number over time. Or rehabilitated criminals. How do we change our rehabilitation programs in our correctional facility to ensure that we have the maximum and optimal number of rehabilitated individuals that leave prison, that leave zero possibility of them relapsing and becoming criminals again? So from the determination of these equilibrium points, we then get the criminogenic potential threshold. This threshold is used to measure the potential of a criminal being born or a criminal being created, if I may say. So that is the rate that helps us understand crime dynamics better. For instance, I am now going to define this criminogenic potential threshold as this R naught here, okay? So I'm saying when R naught is less than 1, this means when R naught is some factor between 0 and 1, I am going to have a very low, I'm going to have 0. So remember, CP was our corrupt prisoners, sorry. So I'm saying when R naught is less than 1, that means my equilibrium for my potentially crime-free world would be stable. But if R naught is greater than 1, that means if we multiply whatever factor that we have, this R naught, by the population of corrupt criminals that we have, then it would be unstable, then our crime will increase. So that is just an example of how this criminogenic potential is used to describe the qualitative change in the system's behavior. And that is the bifurcation that Cindy was talking about earlier. So I don't really want to go into the deep mathematics of how all of this is done, but really, if you are really interested, feel free to reach out and we'll dive more into this. And so after we have our model analysis, we then get into our results and the interpretation of these results. So the interpretation of these results give us a physical or a graphical representation of what would happen if any of these parameters and variables are changed and decreased. Let me see this. Oh yeah, so these are the kind of simulations that help us see that what happens to my graph if I increase a certain parameter, or what happens to my graph if I decrease a certain parameter. What if these two parameters work hand in hand to change? And that is how we use optimal control to see which of the variables are most sensitive to change and potentially increasing or decreasing a population that we are interested in at that point. And yeah, I think that is where I stop. Thank you so much for listening. The pretty mathematician is now signing out, but still leaving the floor open to any questions that you guys might have.
Thank you so much for that informative talk. I must say, some of it went over my head, but thank goodness I'm not the only scientist that is interested in these methods. There's a comment from Sean. He says, awesome talk. I really learned a lot. I'm happy with mathematics being linked to social sciences. This will help me explain the patterns that lead to crime in my neighborhood. However, I might have missed something. How do you test whether a systems-based model of social behavior is actually accurate enough to trust, especially when human behavior is so messy, as you actually alluded to this, and the data is incomplete? So this is when you're dealing with information that is not measurable. Would you have an answer for us?
I hope so, because that is what I am dealing with as well, to be honest. Because I am modeling crime dynamics, I can't really validate my experimental data through comparing it with already existing data, because to be honest, our crime stats are not reliable. You know, we've got dockets missing or just inconsistencies in reporting those crime data. So now that's when the intuition comes from. That's when we need to validate whatever you have intuitively, and which is where the simulations come from. So now I'm going to put my differential equations, whatever model that I have, I usually put it into whatever program I'd be dealing with then, like Python or Mathematica or whatever, and I have it create a simulation of all my different population classes over time. And if it makes sense intuitively, if I can see that, okay, it only makes sense for a susceptible class for the population to decrease until a certain point, it only makes sense for a criminal class to decrease until almost zero if everyone is getting arrested and stuff like that. So I'm saying if my simulation looks good, if it looks normal, if it looks like this is really what could happen in real life, that is the kind of outcome that I'm taking from the result. I don't know if that answers your question. So the simulations help with that, basically.
Simulations help. Would you argue that, also referring back to, say, specifically for your topic, if you work closely with criminologists that are in the field, experts, so to speak, could that also assist in your intuition? Would you find something like
100%.
that?
100%, because then I think that would also help in not making so many assumptions, because they would have more insight as to how these people behave.
This is definitely what we're looking for in social sciences, the ability to work with people that are doing pure maths, that are able to, as much as you call it intuition, but it's very calculated education that you rely on. You're absolutely being coy. Audience, if there's anyone else that has a question, please raise your hand and unmute yourself, or you could type in the chat. But just to close off Sean's question, he says that, thank you for the first answer, it makes sense. And for the social sciences like me, who have never done modeling before, what's the best first step in learning the basic concepts, working with existing models? Or is it collaborating with modelers like yourself? Or what tools or resources do you recommend? Help us out.
I would definitely first recommend collaboration. We're always looking for different things to model and different perspectives to go into hand. Collaboration is definitely the best. I think you learn more in collaboration as well, because now instead of you just learning whatever new method there is on your own, in a collaboration, you actually get to implement it in real life, making sure that no step is missed and anything like that. But other than that, there are a lot of modeling crash courses that I also attended when I was doing my master's. I'll just find out if we have any more, especially from my HOD, who's an expert at crime dynamics, one of the very few experts in South Africa, actually. I can ask him if he can share any other workshops that we have for the rest of the year, maybe then I can share that with you.
That'd be perfect. But for people that are outside of UJ, I heard you talk a bit about Python. Is there any other package that you would recommend for us? Specifically, I'm interested in your output. Your graph looks amazing. What package did you use for that?
I got this from my supervisor, to be honest. Let me not take credit, that is not mine. I got this from a supervisor, but here he was not modeling crime dynamics per se. So here it was a model of HIV, how HIV moves inside, how the virus population basically changes inside our body, if I may say that. But here it looks like he used, this looks like Mathematica, which is another programming language that we use as mathematicians. So there's many programming languages. We have Mathematica, we have Python, like we said, there's R, there's, all of this can be done in all these languages.
Okay. Maybe we could invite your supervisor also to share more about Mathematica. Put in a good word for us.
100%, 100%.
All right. Jen has a final question for us, and then I think we're done for our Africa Tech session. Go ahead, Jen.
Hi. As I might have missed it because, as Cindy said, a lot went over our social scientist brains. But I wanted to ask, what do you do with these models at the end? Like, is this about like manipulating different variables and trying to see like what happens and figuring out like, oh, this might change the outcome? So like with the criminal behavior, so this might like reduce the chances of someone becoming a criminal. Yeah.
Definitely. Sorry. Yes, so it's for both those reasons. One, just for us to know what is most sensitive to increasing or decreasing a criminal population size, but also as advice to whoever is in authority, our criminal facilities, community leaders, correctional services, whatever that we have. We are trying to build these models that can be used as part of creating better interventions for hopefully sorry, what's this word I'm looking for? We're just trying to eradicate crime, for the eradication of crime. Yes, if intervention strategies for the eradication of crime.
Okay. Okay. And like, how do you come up with your list of variables that you would plug in? Is it just like you plug in as many? Is there a limit to how many variables one could use?
Definitely not. So, like in my system, I just had a system of 5 differential equations. These systems can go up to 20, 40 equations. So there's definitely no limit. And the more variables you include in your model, the more accurate it is, honestly, because then the less assumptions that you make.
Okay. Okay. Thank you.
Thank you, Jen. Last question from Kevin Igwe. Please go ahead, Kevin. Oh, I see that Kevin left us a question in the chat. I'll just read it on his behalf. He says that awesome presentation. Thank you for this. Then he comments and asks a question. Crime is more about individual than group. With that said, I would like to understand what informed your use of SIR over the methods like ABM. Thank you, Kevin, for your question.
All right, that is completely true. So, like I said, there are so many factors that can be included in all of this, but honestly, that would just complicate your model even more. So, I chose the most basic one, which is just crime spreading as an infectious disease, because to me, that was really the easiest way to show how crime spreads, honestly. And there's nothing wrong with using ABN. One is not more accurate than the other. I actually think the ABN ones are more accurate than these SRR ones, because for the SRR ones, to ensure my accuracy, I would really have to compare it with data that we have available, which I am not doing. So this is no different. I hope that answered your question.
Yes, you did answer my question. My apologies. Can you hear me?
Yes, I can hear you, Kevin.
Okay, my apologies. I was trying to switch on my microphone and I forgot how to use computer. My apologies. Okay. You've answered my question, and I just want to ask a little bit more on that. Obviously, I understand this is what you've worked on, and obviously you know a lot about this. Did you ever compare the SIR model with any other model and see how it performs? If you want to do that, how do you think one can do that?
No, I have not. I have not worked with any other model. I've only worked with SRR models for the specific reason. Research, sorry.
All right. It's for me. For me, it's not more about question. I think it's more about curiosity from my side. Because I love your method. I like it so much. It obviously tells us about population, but like I did say, thinking about crime, it's more have to do with individual behaviors. And my understanding is that ABM will allow you to check how individual behaviors actually affect the model or even the population, and how isolating certain type of behavior can help the community combat crime. Because assumption in the criminal space is that if you maybe put someone in prison, then there will be crime will reduce in the community. But sometimes we see that we put someone in the prison, and for the fact that you remove that person, somehow, as human behavior may be, and other people see it as a space for them to actually venture into the criminal and become the kingpin, because the former kingpin is gone. And that dynamics hasn't been tested. I'm just curious, with ABM, such kind of dynamic can be tested. And I'm just like, if you happen to supervise me as your master's student, maybe we can work on it. Thank you.
Oh, that is amazing. Thank you so much for that, Kevin. But I was thinking about it now as you were speaking. I think as you're saying, how crime is more like on an individual level than a community level. So looking at our susceptible class, moving from susceptible to the criminal class, like you're saying, because of the different reasons from different individuals, you could have many other subclasses for criminals. You could have the one flow that goes to the first class of criminals, like maybe these became criminals for these reason, or susceptibles becoming criminals for another reason can be in a different class, and so on and so forth. So you can have different classes for all those different reasons of criminal activity. But yes, I definitely would not mind diving deeper into this with you. That would be really amazing.
Thank you very much.
Okay, it seems like you have a student that's ready to enroll.
I received.
This is great. Thank you so much, everyone, for tuning in. Thank you so much for everyone who's on our YouTube channel, everyone who joined the actual Zoom webinar. We will see you again. As you know, this is a bi-weekly session. During your lunch, have your sandwich while you're learning something. Thank you so much, Pretty Mathematician, for joining us. Thank you so much, Methods Lab community, to join our very first 2026 webinar. You have a lovely day. Goodbye.